Hello, this is Tom. Today I wanted to talk about scaling. So, this is a pretty big topic, so I thought I'd give a little bit of an idea of what I've been doing for the last couple of years and show you the results I've been getting. I think that would be nice. So, when I first started looking into scaling of this stuff, what I realized is that there wasn't really anybody that measured it. So the first thing I did is altered a full node client and started putting code in there to measure exactly what took time and how much time it cost. So what I did is take the Bitcoin Classic client. This was back in 2016, and I realized that about 80% of the time was spent in the UTXO database, the unspent transaction output database. And this UTXO database is basically you do an insert when a new thing becomes available for spending. You do a lookup to see if it actually is, if something is still available for spending, and you do a delete when it no longer is spendable. Very simple operations. When I started looking for how to speed this up, the first thing I tried was take the current database, which is LevelDB, is that I wanted to make it parallel. So I put a couple of locks around the right parts and started making sure that I could use the UTXO from different threads at the same time. Turns out this didn't really have much of an effect. It was a couple of percent faster. So okay, that was nice, didn't work. And I started to realize that the only way forward is to come up with a different database. And to do the research there, I actually started looking into existing databases. So I tried a Postgres, MySQL, an in-memory database, SQLite, and I tried different attempts. One of the things I tried was just to insert it, and that was ridiculously slow. So instead, I thought I was going to be really smart. I was going to have a bit of a trick, because I realized that the really wide keys, the 256 bits TX IDs that you need to look up with, were really difficult for the database to handle. So I was going to split that up into an integer. Real SQL database experts are probably going to laugh at me, because I did it on an actual column. There's probably much better, as faster ways to do the same thing. All this experimentation, and I tried different connections at the same time, led me to a simple conclusion that there was a basic design in SQL databases that was not useful for us. Specifically, that when you write data to the database, it waits until the data has been stored to disk before you can do more operations, or before you can commit. And this waiting until it's saved to disk is extremely expensive, because then you're going from something in memory to the disk speed, and disk I/O is probably like 1,000 or 10,000 times as slow as doing the same thing in memory. So it's basically just starts waiting for ages to do anything, which kind of destroys your whole scaling proposition. So I realized there was an incompatibility here, and that doesn't work. When I started looking at alternatives, I ended up realizing also that most SQL databases really didn't do multi-threading very well. you can open multiple connections to a database, but what you do in one connection won't be visible in the other until you commit. And then we come back to the previous problem where you end up waiting for the disk. And it's like, okay, but that kind of defeats the purpose of having multiple connections or multiple threads. So everything is always serialized into one stream. It's like, okay, but I really want it to be multi-threaded because that is the main way of scaling in the last 15 years of CPUs. You probably can't find a single core CPU anymore. And so I started looking into this, how to solve this. And at one point I woke up on a Sunday morning and I had been reading about internal data structures, because when you look at standard collections in standard C++, C#, Java, and all those things, you have standard collections. Those are things like hash maps, and they are lists and all that stuff. A hash map is really useful and people know how to use it, but how is it built internally? Well, I figured out at one point all the little details and thought, hey, this is actually extremely useful for a very specific database, because what I'm looking at is we have a transaction ID and an output. That is basically how a transaction in Bitcoin Cash refers to the previous transaction that it's spending. Transaction ID and which specific output it is spending, it's taking money from. And so when you want to do a UTXO database, those two properties together make the key. And when I want to have a database that essentially shows, hey, my output still has money on it, that's the key I have to look up. So that's basically my key in my database. And when you look at a hash table, the hash is basically how do I explain this easy? So when I look at a hash table, it is built up from having a long list of so-called buckets, and each bucket has an ID, and this ID is basically a hash. Typically it's a short hash, like 64 bits instead of our 256 plus the output. So what I did in my design of UTXO, and as I said, this was basically something I started writing down on a Sunday morning, is, hey, what about I create a table that is large enough, or a list really, that's large enough that is my lookup table. And each entry in that long list is, say, for instance, 128, or 0 to 128, so 7 bits. And I take the first 7 bits of the hash, because that's a random number, and I map that to that specific entry. So I don't really need to have any of the complexity of a hash table, because I just take the hash key, my transaction ID, and I instantly map that by just cutting off the rest to a simple flat list. And in that flat list I then store a long list of everything for duplicates. So I tried to play with this. I wrote the code, and of course you still want to store more than 127 items in there. So what I ended up doing is trying and playing with how big I could make this. I ended up with a list of 1,000,000 entries, because this was a nice amount that kind of made sense to me at the time. and looking back, I think it was a sane decision. So I have a million entries list, and every transaction is a transaction ID. My key is instantly mappable to one of these entries by just basically cutting off the rest. No operations done, it's free. So when I find one entry in my lookup list, all I have to do then is provide a secondary list where duplicates go, because there's going to be more than one transaction ID that has the first so many bytes that map to my million entries list. So a bucket, and in that bucket, that list of IDs is there for me to look up and find what the actual result is. So the way that I map this is actually extremely cheap, but the thing I didn't have at that point was enough entrances to have the entire UTXO scalable. No. So this two-step idea actually worked really well, because I have one list that is just, stored on disk, and then my buckets I actually store in a file. So what I realized is that when you have the so I went to my second step, and this is actually very funny. When I started looking at the SQL databases earlier, I realized one thing was really slow. The writing saying this is my point, my checkpoint really, and you had to do that all the time in SQL database. You didn't really have a whole lot of options unless you started doing it all in your client. Then you couldn't really depend on the SQL database anymore to, for instance, do a lot of caching. It became a bit of a mess. Multiple levels of cache. So what I ended up realizing is, if you have a blockchain, you basically download some data from the internet, that is your block, and you start validating it. Now, if some time during this whole process your power suddenly goes off or your hard drive dies, then essentially you can just go back to the previous block, because you can just download that data again. This is the beautiful thing about blockchain. You can even be, a week behind, and all you need to do is go back to the previous point that you're sure is stateful and just replay the blocks. And I was thinking, hey, wait a second. This really makes a lot of sense in order to allow me to build this database on the same principles. So when I start inserting stuff and deleting stuff, I end up modifying buckets. Now, if I don't actually overwrite the previous version of that bucket, then I can save, hey, this was the state now, and yeah, I've done a lot of work then, but that wasn't really something I'm sure about because the application crashed, the power went off, or something like that. This is what I'm certain of, my checkpoint. And when I realized all of this, it started to become really easy to decide that for my UTXO database, I was going to have my long list of lookups. Then I was going to have buckets, and every change of that bucket was stored in memory for a while in order to allow multiple changes to not end up with multiple writes. But then I would continuously write buckets to disk, and instead of overwriting the previous one, I was just have a log file idea, which is a continuous appending of data to that file. So you would have maybe 10 copies of that same bucket in slightly different states in that file, but you only have to look at the last one. and your lookup table just points there. So your million item list just points to the latest one, and therefore you have a very simple way of rolling back because you have a copy of that million item list that points to a previous one. Problem solved. So at this point I started thinking about multi-threading, because the saving would be nice to be done in a different thread than the inserting. So I could continuously insert, which was basically just, the validation of transactions, inserting new items or deleting new items. And from the point of view of my UTXO database, they were just changing buckets. And the updated buckets need to be saved. Now, this is something you have to do in one, or it doesn't make sense to do it in multi-threads because you end up waiting for disk. So that was one thread that pushed stuff to disk and just waited until it's done and then pushed more to disk. Very simple concept. But multi-threading. My design is initially just had mutexes, and that makes it not very nice because you still end up waiting on the other item. So I started looking into how to make this lock-free. Lock-free is a concept that you use atomics for, and it's well researched. There's lots of good stuff about it, and most of the time, the fun thing is that for good multi-threading, you don't really find a lot of pre-made libraries or containers. And that's because if you want to do it well, you have to actually understand the concept and understand the trade-offs in order to have a fast system. Otherwise, it's just cheaper to use the simple locking mechanisms. So what I needed to do, instead of just getting a library, is to educate myself. And I ended up watching a lot of videos about this, and I found a fantastic data structure, a design really, which was based on atomics. It's an atomic pointer, and the idea is that if you have a atomic pointer, that you can do two operations on it, which is one is to allocate and one is to release. So somebody can take exclusive ownership of this pointer, and a pointer can be, some data structure. The idea is that you have a list of items, and one of them is the thing you want to allocate or take ownership of, and it points to some data structure. What you do to take the ownership of it is you take an atomic operation and you change the current to insert a null pointer instead. And when that succeeds, now the table is a null pointer, and that indicates to everybody else that, hey, this one has been operated, has been allocated, has been locked, and you can't use it. And the beautiful thing about atomics is that it makes that change from not allocated to allocated safe and lock-free. So I figured, hey, I made this list before. That is, that million item list of pointers to buckets. I can make that a long list of atomics. And at first I was like, well, a million atomics, does that scale? And I realized very quickly that really an atomic is not some special thing. The CPU doesn't know about it, other than that the compiler generates some more instructions. There's not some global list of atomics. So I was like, okay, so that actually could scale. So I figured out, I try it. I replace my standard list of 1 million items with 1 million atomics and made each of them point to a bucket. Okay. What this this cost me some effort to do correctly. As you can understand, it's not simple matter, but the concept is quite simple. And the effect is that now I changed from having one point where the different threads can come and say, hey, but I have to wait for this other guy, to now make that chance much smaller. Because a thread can come in and say, well, I want to reserve and update that bucket there. Let's see if I can take ownership. And there's a 1 in a million chance that somebody else has already taken it. Because there's a million buckets. And so it is effectively very close to being lock-free, or it is lock-free, it is close to being perfectly multi-threaded. Now, of course, there's some trade-offs here, as all systems have, because you end up writing to the mains memory more often in order to do the synchronization, but that's essentially the cost of any sort of solution, so that was very acceptable. So then I came to the next step, where I realized that if you want to modify a bucket, that means you have to read it, you modify it, and afterwards you have to write it back. Okay. But then you're going to end up with scaling issues when you read them into memory. Wouldn't it be much nicer if the data structure on disk is identical to the data structure in memory? Because then you can just do a memory map. And it makes it zero copy, and zero copy means no overhead in all that encoding, decoding, and all the things you can come up with. So I figured, if I make a slightly smarter data structure that is a bucket, then all I need to do in order to read it is point to a specific location on disk using memory mapping. So in order to read from the UTXO, there is no copying. It's just a simple read. Now, if I want to delete something, that means I have to copy it into memory, modify it, and write it back later. But if I just want to read it, for instance, if I want to do a lookup of the UTXO and find out where data is, that is free. Well, it still has the disk I/O, but other than that, it's free. So this was a very attractive proposition, and I ended up with reusing my previously designed CMF, which is the compact messaging format, which is people will see a lot of similarities with Google Protocol buffers, because it basically tries to have the most compact way of encoding data. And this is relevant too, because, as I just said, we're waiting for a disk I/O, right? So if you have the data as compact as possible on disk, you can have, with a single read, you can get the most amount of records into memory. Because as the way of how operating systems handle things like memory mapping is that they read one block, and one block is typically 4 kilobytes. So you want to have as much data in there, and practically all buckets should then fit inside of one block, or in the worst case scenario, it's going to be on an edge, and then you need to read 2 blocks, and that's going to be slower. So you want to make sure that you have the most compact amount of data in how you encode this on disk. And because of the previous requirement of having not to read and decode it, it also means I have to have the most compact way of remembering it in memory. So I made myself my life very difficult there, and it took me some time to get that all done properly, but it works really well today, so that's I'm very proud of. So you can read transaction output, one record in your database, by basically providing the key, which is your long transaction ID. It takes only the first couple of bytes, looks it up in that long list of 1,000,000 records, which is my hash table, and it figures out if there's an in-memory representation already. In that case, simple, done, that's a 1-bit change. If not, it knows exactly where on disk it is, because the pointer is just an item on disk. And if it is on disk, it reads it in memory by locking it first, reading it, and the operating system will read it from disk for you. And at that point you have the full data, because a bucket is just a list of transaction IDs at that point. And of course I made those sorted, which means that if you have a really long bucket, really big bucket, it's still quite fast to go through. And at the end of that list of tasks, what you have is a pointer to a block height specifically, and an offset in block, because that's where in the end you can find your data. Because I don't currently copy my output script into the UTXO. That's a caching feature that I really want to add later, because it would help, but probably not as much as people think, but it would enable pruning. So that brings me to my next section of scaling, the UTXO database. That in my checking, I realized that when people spend money on the chain, it is a nice curve of how old those transactions they are spending. And the vast majority of transactions they are spending are quite recent, like a couple of days, a month. And so if you look at the fact that we now have 10 years of history, we will benefit if we chunk that up. If we basically take the most recent ones and do the lookup there first, and then when that one fails, we look at one before that and see if it failed, if the transaction is there, and we go backwards in time. And so if we make that lookup cheap enough, then we can scale forever, because all you need to do is add a new database at the end every year. Let's talk about garbage collection for a moment. So in my design, as I explained it, what I ended up doing is appending new versions of buckets to the file all the time as I write them out. And the reason for this, as I explained before, is that I don't want to overwrite something, because I want to be able to go back to a previous point in time. So what I end up having is an ever-growing file. Now, of course, this is a bit of an issue, because you don't want to just continue writing forever. You need to do something about that. And if we look at virtual machines like Java, they invented the concept of garbage collection. And what this does is it copies all the actually referenced items and creates a new list, a file that is obviously much smaller, because you just changed all the different hundreds of revisions of one and replaced it with just the one. I chose to have a file that is 2 gigabytes, which perfectly fits in an assigned integer. and when that one is almost full, I end up copying it into a new one. In When I was trying this out, the resulting file compresses from about 2 gigabytes down to maybe 300 megabytes, sometimes 500 megabytes. So that is a very good indication of how often I end up rewriting stuff. I think that could become better if I store more buckets longer in memory before I write them out to disk. But this is a further research topic. So every now and then I need to copy all the buckets into a new file, and I call this garbage collection step. What is really important to realize here is that this really doesn't happen very often. If you have an operating node, this happens maybe once a month, maybe once every 4 months. And so maybe something can be done to do this when we know it's a quiet moment, in order to not block the system for a couple of seconds. I don't know if it's worth it. One of the optimizations I've been working on as well is when I do my first level lookup, I look in this long list of buckets, the 1 million items bucket. And my million items can very quickly tell me, no, this is a transaction ID that is not known by this database. But if I don't have that, I have to do a second lookup, and therefore I have to check my actual bucket. What would be very useful is if all the buckets that are directly accessed are stored very close to each other on disk. Because then if you get a new block in that needs to be validated, you very quickly do the lookups, and you only have to read that small amount of data, and so the next transaction that comes in might give you a hit or a fail without actually having a disk I/O option, because it's already in memory. In other words, you want to keep your data close to each other, because that avoids you having to do multiple reads. Simple said. So this was the overview of the UTXO database. It literally is a new database style. It is based on the concepts of blockchain. Every so many records, it specifically syncs to disk all the items, and this means that if you have some sort of data corruption, the database correctly reverts to one of the 10-20 different past checkpoints in order to try to find a stable base. And of course, what as part of those checkpoints, we also write which block we were at. And so getting from that point in the past to now is essentially just replaying of the blocks we already have. Since this is an actual proper new database type, I also wrote various command line tools in order to inspect, to dump, and to do things like garbage collect and other optimizations on the databases, which is just nice if you want to have a simple way to do a UTXO lookup and you're not entirely sure if it has to be the latest version. Then you can ask the database from the command line tool too. That's kind of cool. And I think that kind of is the overview of the UTXO database. As I indicated, this is the part, the component that takes by far the vast majority of time in validation process. It's actually interesting to think about how harmful it is to not copy the output script of transactions in there, because yes, it takes much more effort to look up not just a transaction, but also the output script if you want to verify it. But when we look at the actual usage, a node will get all of the transactions in between the blocks, and when a transaction gets entered into the mempool, it will have the UTXO lookup because it wants to know that this is a correct one. It will actually look up the script at that point, do the validation of the script, and see it's a valid transaction. It goes into the mempool. When at some point later that transaction happens to be included in the block, we do another lookup, which is reasonably cheap because we already did that before and we cached some information, and then we delete it. And so at no point during the actual block validation do we need to look up the output script again. We already did that in the past. It's in the mempool. And so the separation of that and going back to the initial idea that Satoshi had of just storing in the UTXO a pointer to the transaction in the blockchain is actually not a bad idea. The idea of copying it still is something relevant. Copying the output script and the amount and whatever you need to do the validation is still relevant, for the simple reason that if you don't do that, you need to keep the entire blockchain, the historical blockchain, and that means you can't do pruning. So my idea, what would probably be useful research project, is that we have a separate, let's call it a cache, where all these things get copied into, and we can, do some sort of garbage collection there too, where we throw away the ones that are no longer needed, and that way you're completely separated from the actual blockchain. You just have your cache of output script and amounts and whatever, and the UTXO as a separate part. But maybe it shouldn't be inside of the UTXO itself, because that just makes it bigger. So this is something that, as I said, it works really well right now. It's not really needed. If you do if you want to actually fully validate a huge amount of data, it's slower because you need to do that extra lookup, that extra read. But this is not the actual usage. So is this really needed to, put time into? And I think that ties it back to the initial point of what is scaling. The UTXO is the main bottleneck, I said. Let's refine that a little bit, and I concluded over the years that what really is the bottleneck is realizing, first of all, that we are talking about a huge amount of data. The blockchain is something like 160, 170 gigabytes right now, and this can't be in memory. If you just look at the UTXO, it is currently something like 3 gigabytes. It's really not that big. This is again without those scripts, and this we can mostly keep in memory, but you don't want to do that because then you basically you're not ready for the future, let's put it that way. So you want to have good caching, and this is what I mean with what is the real bottleneck. The bottleneck is data locality. If everything is in memory, it's pretty darn fast. The moment you start putting stuff on disk, you have to realize how many reads it takes, how many disk I/O actions it takes to get all the information. And if you go one step further, it means that if you have the UTXO on one solid state drive, and you have your blockchain on another, and you need to do that 2 lookups, then you should put them on 2 different SATA ports to make those IOs be parallel, not serial. So there's a lot of little details that you want to take care of if you want to look into the future for scaling. I think if I look at how I tested this, I've tested the UTXO database on a Raspberry Pi. It's being tested on a Xeon CPU that's like 5 years old, on a AMD Threadripper. So that's 64 cores that you access this database in parallel with, which actually works really well, because one of them is constantly saving and the other ones are just doing lookups and stuff, and it scales really well. And on these, if I just look at the UTXO database, then I've seen on 2019 hardware 20,000 transactions per second, which every transaction has multiple inputs. I didn't do an actual count, but it's going to be a multiple of that, of actual lookups and inserts being done every second, and that works really well. And I think that means that with this design, and you know, it's not a final design, I'm not going to say I'm perfect, I think we can move towards world scaling. And this is something that is very exciting to me, and I hope more people will actually try to look into this technology as open source and see how we can actually start using it in production.